We're now going to talk about the interaction of the vertical and horizontal surfaces on a tail. And these interactions are pretty complex, and so we don't have any really simple equations that we can use to capture these. And so basically, most of the time, you're going to need to go and use some kind of software. Now, what I'm using here is called Mockup, and it's a free online piece of software that you can use from this website. You can see up at the top here. And basically, this uses a numerical lifting line algorithm and can account for the aerodynamics and interactions of wings that are placed relative to each other. And so what I've done here is just created a vertical tail and a horizontal tail. And maybe it's not too pretty, but we'll be able to see the interactions just based off of this kind of a geometry. And so I can go into components here. Wing 1 is my horizontal tail, and I've set that to have a root airfoil that's a NACA 0012 with zero lift angle attack of 0, and so basically a symmetric airfoil, right? So we could zoom in on this. You can see that's a symmetric airfoil. And so at 0 degrees angle of attack and 0 degrees side slip angle, this system should produce 0 forces. And that's because I've also set this vertical tail to also have a NACA 0012 airfoil. Okay, so symmetric airfoils on both of these just to for this demonstration. All right, so this is the system that we're looking at. And then I've opened another tab where I have the identical system, except that I've deleted the horizontal tail. So we're going to be able to see the influence of the horizontal tail on this system. Okay, so then in this, we've got a components tab and then an analysis tab. In the analysis tab, I've set these both to 5 degrees angle of attack, 5 degrees side slip angle and 0 degrees angle of attack. And you can test this. Actually, let's just do it right now. If I put in 0 for both of these and update results, then you can see down here at the bottom, I'm going to get 0 lift. This is a lift coefficient, a side force coefficient, rolling moment coefficient, yawing moment coefficient. You can see those are all 0. Now, I'm getting non-zero drag because it's accounting for some parasitic drag on this airfoil, and because this wing is placed above the center of gravity, which is that red ball down there, I'm also getting some positive pitching moment. We're not going to be concerned with that here. We're mostly concerned with the effect on the other forces and moments. Okay, so I'm going to put this back to 5 degrees beta, and then update results. And so you can see that if this wing were flying all by itself at 5 degrees side slip, then it would get 0 lift. The side force, C sub y, is this minus 0.2658 down here. And we're going to get some rolling moment. And that rolling moment makes sense because our wing is placed above the center of gravity. And so the lift that's coming off the side of this is above the center of gravity. And so we'll get some negative rolling moments. That makes sense. And we're getting 0 yawing moment. Okay, so that's with this wing all by itself. And now let's put that same wing in this system here, but with the horizontal stabilizer, and put it at the same side slip angle, 5 degrees there, and then 0 angle of attack, and update results. Now I should say what I've done here for these for this reference area, I'm just using the reference area of the vertical stabilizer for all of these forces and moments so that they're comparable between the two systems. So these coefficients only make sense relative to the area of the vertical stabilizer. Okay, you can see now though, when we add this horizontal tail, we're getting some lift coefficient, which previously we had 0 lift coefficient. You can see that CL equals 0. Well, now we're getting some non-zero lift. We're going to talk about why that is in just a second. The drag we're not too concerned about. The side force, we're getting minus 0.3216. That's actually a little bit more side force. Remember, side force is positive to the right. And so this is a left force, which makes sense because beta is positive from the right. And so we're getting lift in the left direction here, but we're getting more lift in the left direction, or a larger side force on this configuration here with the horizontal tail. We're getting a rolling moment that's actually slightly less than the rolling moment that we got before. Remember, the rolling moment is due to the lift vector from this vertical tail is sitting above the center of gravity, or that side force vector is sitting above the center of gravity, and we can see that the rolling moment has actually been reduced once we added the horizontal tail, and then we're getting some non-zero yawing moment now, where before our yawing moment was exactly 0. So let's look at this in a little bit more detail. What I've done is just copied down here the values for the lift, the side force, the rolling moment, and the yawing moment for each of these configurations. So this is the horizontal, or the vertical with the horizontal, and then this is a vertical tail all by itself. So these are the values here. So let's talk about what is happening on a when we have some interaction between a horizontal and vertical tail here. So if the horizontal tail was not there and we had some 5 degrees side slip angle, then we would get a lift distribution here on the vertical that looks something like this. Now, because once we add the horizontal tail, though, this actually acts as a giant winglet, so to speak. If this were the wing, then this would be a huge winglet. And so what happens is that the lift actually doesn't go back to 0 there at the juncture. So what happens is that this lift is now going to have some finite value here when it meets that horizontal tail. And so we actually have an increase in lift, or in side force, and we can see that here. We actually have more side force, minus 0.32, instead of just minus 0.26 when that tail was all by itself. So we have an increased lift in that direction, and so we get a larger side force. And on top of that, because we have low pressure, remember we have low pressure on this side of the tail, high pressure on this side because beta is coming from the right. Let's just draw that in here. So beta is coming in here from the right. And so we have high pressure here on the right-hand side, low pressure here. Well, that low pressure actually induces a low pressure on the upper surface here and a higher pressure here, okay? And it induces a higher pressure right here in this juncture because we have high pressure along here. Some of that's going to bleed over. We're going to get some high pressure here, which induces actually some low pressure down here. So what we'll get with this interaction is that we're actually going to get some lift on the horizontal tail that might look something like this. Okay, so these are, we're going to have little lift vectors going like this due to that interaction of just pressures on the surface. So so this now explains why we're going to get some positive lift in this overall system. And I've drawn these equal, but actually the lift on this side would be greater than the lift on this side. So that's a little bit misdrawn here, but that's why we're now going to get some positive lift overall, is because we get some really low pressure on this side that induces some force in the lift direction, and that low pressure will be greater in general than the high pressure here on the right hand side, or excuse me, the low pressure here on the right hand side. Now let's look at the rolling moment. So before, when it was all by itself, the main rolling moment came, it was offset basically at the center up here, and so we had some rolling moment due to that lift, and so that's what we get right here is this minus 0.13. But now that we've added this horizontal tail, we actually reduce the rolling moment, and that's twofold actually. That's partially because some of this lift has shifted, or the center of the lift from this vertical is shifted down a little bit, so the moment arm is less. But also, because of this low pressure right here, we have some rolling moment actually acting to induce a positive rolling moment. The lift up here is inducing a negative rolling moment, and the lift right here along this horizontal is inducing a positive rolling moment. Now, I should have said at the beginning, we're looking at this tail from the back side, okay? So we're looking towards the front of the aircraft, and so that's why beta is coming in here from the right. We're looking towards the nose of this aircraft, okay? So this was creating a negative rolling moment, and these guys down here are counteracting that a little bit, and so that's why we get a lower negative rolling moment. It reduces that slightly compared to the case where this vertical tail is all by itself. And finally, we're getting some yawing moment, where before we had 0. This finite yawing moment can be coming from a difference in lift distribution along the horizontal from the left to the right. And so that difference in lift distribution can create a difference in drag on either side of these. And so that can be creating this yawing moment. Okay, so the interactions here between a vertical tail and a horizontal tail are actually very complex, and it's difficult to just have some simple equation that we can use to estimate things. But one thing the approach that Phillips takes actually in his book is that he estimates the change in side force. Actually, he estimates this change here by basically saying that adding a horizontal tail is like increasing the aspect ratio of the vertical tail, right? So we have an equation from lifting line theory that can tell us what the lift slope of a wing is, CL alpha, and it's a function of the CL alpha tilde, or the two-dimensional airfoil section lift slope, and it's a function of the geometry, so the aspect ratio and the taper ratio, and you can compute all that from lifting line theory. And so basically what he says is we're going to come up with an effective aspect ratio that is greater than the actual aspect ratio of that vertical tail, and by increasing that that increase in effective aspect ratio is due to this large winglet, so to speak, that's acting here. And so he has a plot in his book where he ran a bunch of simulations using numerical lifting line analysis, actually, to estimate the correlation between the effective aspect ratios of these. So that's one way to look at this. And so that basically boils down to a change in lift slope. Either this configuration here has a higher lift slope or a higher change in side force with respect to beta than this one does, and so that's basically, he says, due to a higher effective aspect ratio. And so that's one way to look at it, and if that's useful, then great. Another way, though, would be just to plug this into this numerical lifting line code yourself, or into a Vortex panel code, or into CFD or something, in order to estimate this. And that's a bit more accurate because then you can put in your actual geometry. He had to make some assumptions about the size of the vertical tail compared to the size of the horizontal, for example, and the geometries of those in order to get these solutions. And so, of course, they're not really global solutions. They're just kind of an example solutions that can be used as a first guess if you don't have the time to plug this into a code. But you probably want to put your geometry into a numerical code of some sort in order to estimate these types of interactions that are fairly complex, so that you can also capture the changes in rolling moment and the change in lift due to these interactions.